All right, well, we did the sum rule. We did the product rule first. We did the sum rule. We talked about differences. And we did some combinations. So let's make this stuff more general. Do it? Oh yeah, we did pigeonhole principle yesterday, that's right. So I'll come back later and do more on pigeonhole principle, but I want to make sure we get through combinations and permutations today so that you can have what you need for your homework. So let's start with some definitions. So a permutation is an ordered arrangement of, we'll just say, objects. And an R permutation is an ordered arrangement of R objects. So for example, here's a set of 3 objects. A permutation is an ordered arrangement of those, for example, ABC, or BAC, or CAB. Each of those is a different permutation. A 2 permutation would be an ordered arrangement of 2 of our objects. For example, AB, AC, BA, BC, CA, CB. A 1 permutation would be an ordered arrangement of 1 object, which would be something like A or B or C. A 0 permutation would be an arrangement of 0 objects, which is just nothing. And these are just called permutations, but they could be called 3 permutations. And I think I've listed all the possible 3 permutations, 2 permutations, and 1 permutations. So what do we do with permutations? We can use them to answer these questions that we've been talking about. So for example, pick 3 students from a set of 5 to stand in a line. All right, if we're picking students to stand in a line, the order is significant. We're going to say which student goes first in line, which student goes second, which student goes third. So this is an ordered arrangement of 3 students out of 5. So in other words, we want to create a 3 permutation of 5 objects. So we have 5 objects. We want to pick 3 of them and put them in a particular order. And our notation for this would be P 5, 3. So P 5, 3 is the number of ways that we can arrange 3 things out of 5. So more generally, P n, R equals the number of R permutations of n objects. So what's the value of Pn, R? we can find this using the product rule. So we're starting with n objects. We want to take r of these objects and put them in a particular order. So we're going to have a first object, a second object, and a third object, and so on. So our task, T, place our objects in a particular order. And we can break this into subtasks. T1, pick the first object. T2, pick the second object. And so on. And we're picking a total of r objects, so our last subtask will be TR, which is pick the last object. And we're starting with n objects to choose from, so how many ways can we pick the first object? Right, we can do that n ways. How many ways can we pick the second object? N minus 1. How many ways can we pick the last object? This is a fence post problem. So it's n minus r plus 1 or minus 1, I don't know. But we can write an expression in terms of r. Well, suppose that r is 2. Then our last number should be n minus 1. Right, so n minus, and it looks like it's going to be r minus 1, which is n minus r plus 1. So the total number of ways is just the product. All right, well, let's rewrite that. I'm going to keep multiplying by smaller and smaller numbers until we get down to the number 1. And I'm going to divide by the same thing. So I've just multiplied our number of r permutations by 1. So I haven't changed anything. But now we can use factorials, because this thing on top is the product from 1 up through n. This is just n factorial. And this thing on bottom is a product from 1 up through n minus r. This is n minus r factorial. So there's a nice workable formula for the number of r permutations of n objects. Just n factorial over n minus r factorial. So now if we have 5 students and we want 3, P of 5, 3 is 5 factorial over 2 factorial. So there's 60 ways to put 3 students in line. So if you have Go ahead.
Oh, I was going to say 65 for all ways.
Okay, cool. You write fast. So if you have 6 people and you want to sit them at a table, first, second, third, fourth, fifth, sixth, how many ways can you arrange those 6 people? It's 6 people and you're trying to choose 6 of them in an ordered way. It's just P of 6 comma 6. And this will be 6 factorial over 6 minus 6 factorial. And what is 0 factorial? That's 1. That's convenient. Right? So this is just 6 factorial. And in general, the number of n permutations of n objects is just n factorial, which we kind of already knew because if we use the product rule to arrange n things, it's n times n minus 1 times n minus 2 all the way down to 1. 52 playing cards, 52 factorial, different ways that we can arrange them. We did that yesterday. What if we wanted to pick one person from a group of 6? How many ways could we do that? It's the number of 1 permutations of 6 objects, which better be 6. 6 factorial over 6 minus 1 factorial. That's 6 factorial over 5 factorial. That's just 6. How many 3-letter passwords are there if we only allow uppercase letters? It's just P26 comma 3. We're choosing 3 things from a set of 26. This is if no repeats. If you allow repeats, then it's a different formula. But this is choosing 3 things and putting them into a particular arrangement, but not allowing repeats. All right, so those are permutations. They're ordered, right? So the other concept is a combination. So a combination is an unordered arrangement. So an R combination is a set of R objects, or let's say a collection. From a set of n. So combinations and permutations are almost the same. With a permutation, we care about the order in which these things are selected. A combination is just saying, let's just choose a set of objects from a larger set. So pick 3 students from a set of 5. But we're not standing them in a line. We're not saying you're first, you're second, you're third. We're just picking 3 students from a set of 5. That's the number of 3 combinations of 5 objects. And we could write this as C5 comma 3. And we can use the same kind of logic. So we can pick the first student from a set of 5. So there's 5 ways to pick the first. There's 4 ways to pick the second. There's 3 ways to pick the third. But if we pick students A, B, C, That's the same combination as if we pick students A, C, B, or B, C, A, or B, A, C, or C, A, B, or C, B, A. Those are all the same combination. This is paying attention to the order. It's counting each of those as a different combination. But we don't care about the order. So if we take the number of permutations and divide by number of arrangements of 3 objects, that'll give us the number of combinations. So we have to divide out the things that we're counting multiple times. So how many ways can we arrange 3 objects? Say again? Yeah, it's just 3 permute 3, right? Which is 3 factorial over 0 factorial, which is just 3 factorial. So the number of 3 combinations of 5 objects is 5 times 4 times 3 over 3 factorial, which is going to turn out to be 3, 2, 10. So just for completeness, what are they? A, B, C, A, B, D, A, B, E, B, C, D, B, C, E, C, D, E, A, D, E, A, C, E. I'm missing 2. A, C, D, B, D, thank you. All right, so there's your 10 combinations. So more generally, this will be the number of permutations divided by the number of ways we can rearrange those R objects, which is n factorial over n minus R factorial times R factorial. So that's the number of combinations. Bless you. So the number of 5-card poker hands from a deck of 52 cards is just going to be C52, 5. Because if you have these 5 cards, it's the same as if you change the order of them in your hand. It's the same hand of 5 cards. So the order does not matter. So it's a combination, the number of 5 combinations of 52 things, which is 52 factorial over 47 factorial times 5 factorial. And this is kind of interesting. I don't know of an intuition why this should always be an integer. Right? N factorial divided by something smaller factorial, we can just cancel out the first R terms or the first n minus R terms. But the fact that this remaining factorial will evenly divide whatever you're left with up there is not totally obvious. But here's a indirect proof of the fact that that's always going to be integral because it's the number of combinations, which has to be an integer. This turns out, by the way, to be 2,598,960. All right, got the idea? Permutations, combinations, ordered, unordered. And we have these formulas. For each. And they're really just product rule applied different ways. So how many 8-bit strings contain exactly 3 ones? 3 ones, 5 zeros. It's a reasonable question. So you got 8 bits. Each bit's a 1 or a 0. We want to know how many 8-bit numbers have exactly 3 ones. Why is that? Sounds reasonable.
Well, you could do this in the same way you did the cards, because you have so many 8-bit integers.
Mm-hmm.
And then, how would you know how many of them contain 3 ones?
Yeah, where's the choosing coming in?
Yeah.
Combinations are related to choosing. So here's one way to think about this. Choose 3 bit positions out of 8. To contain a 1. So we've got 8 bit positions, bit 0, bit 1, up through bit 7. And to construct an 8-bit number with exactly 3 ones, we're choosing 3 of these positions to put a 1 in. The number of ways that we can choose exactly 3 of these 8 corresponds to the number of 8-bit numbers we can create with exactly 3 ones. So yes, this is exactly the number of ways we can choose 3 things out of 8. So that's whatever that turns out to be. And before you launch into your calculator and start mashing out these calculations, these are fairly easy to do by hand. Right? Because if you write out what those factorials are, well, we get lots of things canceling. 2, 3, 4, 5, 2, 3, 4, 5. 2 times 3 is 6. This is just equal to 56. How many 8-bit strings have exactly 4 ones? $100 is the first answer. Don't have $100 though. What? 7? 70. Close. How many 8-bit strings have 4 ones? This is a good interview question. How many 8-bit strings have 4 zeros? Same number that have exactly 4 ones, right? Because if a string has 4 zeros, it's also got 4 ones. So whatever this number is, if you add it to itself, you got to come up with the number of 8-bit strings, which is 256, right? So this is just going to be 128.
Have 8-bit strings that have like 2 ones and 6.
Oh, you're right, my bad. Never mind. I was trying to be fancy. But it will be the same as the number that have exactly 4 zeros. Right, but that doesn't divide the space, you're right.
Should be 8 factorial over 4 factorial. It should be 4 factorial and then divide by 4 factorial again.
Well, it's 8 factorial over 4 factorial times 4 factorial.
Yeah,
But when you cancel those, 8 factorial over 4 factorial is not 4 factorial. It's 8 times 7 times 6 times 5. So the 2 and the 3 will cancel the 6, and the 4 and the 8 will give you 2. So yes, it is 70. Who said 70? All right, awesome. But here's something we can say. What is this sum equal to? So this is the number of 8-bit strings with 0 ones, number of 8-bit strings with 1 1, number of 8-bit strings with 2 1s, number of 8-bit strings with 8 1s. So that's equal to 256. It's the number of all strings.
Is that the sequence symmetric?
Yes. Yeah, this will turn out to be equal to this. This will turn out to be equal to 8 7. So this is a little weird. And the 8's not magic. We could plug any number in for that, and we have an expression involving lots of factorials that you add up and you get 2 to the n, which is kind of cool. So there's some symmetries here with combinations. Mostly we're using combinations just to solve word problems. How many ways can you award a raffle prize, award 3 raffle prizes to a group of 25 participants? All right, so it's 25, choose 3. How many ways can 8 ducks finish a duck race if you give medals for first, second, and third place? So it's the number of ordered combinations of 3 things out of 8. So P8, 3. But there's other things we can do, particularly with combinations. So one thing we can talk about is binomial coefficients. So x plus y to the first is just x plus y. X plus y squared, we know it's x squared plus 2xy plus y squared. But let me write this as x squared plus xy plus yx plus y squared. And x plus y cubed is x cubed plus x squared y plus x y squared. Let me not do that. All right, let me just show you what it is. But how do we get this systematically? So you know how to FOIL, right? First, outer, inner, last. So let's write this out. And we can do FOIL on more than two things. If we want to multiply this out, we could do like a three-way FOIL. Take the first and the first and the first, take the first and the first and the last, take the first, last, first, first, last, 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 first, first, last, last, and so on. We're doing all the different ways that we can choose something from here and here and here, multiply them together, and we're adding all of those up. Okay, it's a generalization of first, outer, inner, last. Well, every time that we do this, we're going to get x raised to something, y raised to something, right? And the number of times that we choose the first thing, that's what the power of x is going to be. The number of times we choose the last thing, that's what the power of y is going to be. So for example, if I just do first, 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 I'm going to get x to the 3, y to the 0. If I do first, last, first, I'm going to get x to the 2, y to the 1. And to do this whole multiplication, I want all possible choices of first or last from each of these three terms. There's going to be 8 of them. Well, we can relate this to combinations. Because what we're doing is, let's just look at the term x cubed. Okay, the only way that we're going to get a product that's equal to x cubed is when we choose the first term from this expression, the first from this, and the first from this. X squared y, we're going to get when we choose the first from two of these and the last from one of these. So how many ways can we choose two of these expressions to pick the first term from? We've got 3 expressions, and we want to pick 2 of them that we're going to pull the x from. That's just C3, 2. And for each of those ways, when we multiply it out, we're going to get an x squared, and we're going to get a y. We could do x, x, y. We could do x, y, x. We could do y, x, x. There's 3 ways to do that. However many ways there are to do it, that's going to be the coefficient of x squared y. And xy squared is the number of ways that we can choose exactly one of these 3 things to take the x from, with the others being y. That's going to be C3, 1. And the number of ways we can choose 3 of these things to take the x from, that's 3 choose 3. And the number of ways we can choose none of these things to take the x from is 3 choose 0. That's the coefficient of y cubed. So it turns out if you want to compute x plus y to the n, you get x to the n, x to the n minus 1y, x to the n minus 2, y squared, x, y to the n minus 1, and y to the n. And it turns out these coefficients are just binomial. They're just combinations. So this is something called the binomial theorem. And these are called binomial coefficients, and they're really just these combinations that we get from choosing things. Well, this ties into something you've probably seen. So who knows what this is? Pascal's Triangle. Look up a picture of Pascal. Tell me he doesn't look like Squidward. One of my students pointed that out. It's eerie. All right, so Pascal's triangle is a triangle that shows you what the value of different combinations are. So let me give you a shorthand here. Cn comma r is written like this. Just n and r on top of each other inside parentheses. Okay, so that's a shorthand for Cn comma r. And it turns out that Pascal's triangle is 0, 0, 1, 0, 1, 1, 2, 0, 2, 1, 2, 2, 3, 0, 3, 1, 3, 2, 3, 3, and so on.
There's some way of getting Shapinsky's out of that.
Oh, yeah. I don't know that one. So these are the coefficients of binomial expansions. We can pull those right out of Pascal's triangle. So if we want to know what x plus y to the fifth is, it's just x to the fifth plus 5 x to the fourth y plus 10 x cubed y squared plus 10 x squared y cubed plus 5x y to the fourth plus y to the fifth. And I just pulled out the coefficients from that sixth row of Pascal's triangle, because that's exactly the combinations of 5 taken n at a time. And Pascal's triangle is easy to draw. The edges are always 1, and the interior is always the sum of the two values above it. So 1 plus 1 is 2. That's the next row. 1 plus 2 is 3. 2 plus 1 is 3. That's the next row. 1 plus 3 is 4. 3 and 3 is 6. 4, 1. 1, 5, 10, 10, 5, 1. 1, 6, 15, 20, 15, 6, 1, and so on. And you can impress your friends and just go crazy with this. And so there's an additive way to get the number of combinations, again, which have all these factorials in them, by simply taking the number of combinations of a smaller number of things. So that's kind of cool. Now, if we take our first row is a 1. Our second row, if we add those together, we get 2. Our third row, 1 plus 2 plus 1 is 4. Our fourth row, 1 plus 3 plus 3 plus 1 is 8, and 16, and so on. The sum of each row is always a power of 2. And that's just this thing that we did a little while ago where we looked at the number of n-bit strings with exactly r1s. So the number of 8-bit strings with 0 ones, 1 1, 2 1, 3 1, 4 1s, 5, 6, 7, and 8 1s. And if we add those up, that's the number of 8-bit strings. It's got to be 2 to the 8th. So we have this nice feature that we can just add each row, and that gives us the nth power of 2. So this is just taking the sum. What if we add squares? So let's do the sum of the squares. So 1 squared is just 1. 1 squared plus 1 squared is 2. 1 squared plus 2 squared plus 1 squared, That's 1 plus 4 plus 1, that's 6. 1 plus 9 plus 9 plus 1, that's 20. And let's go one more. So 1 and 16 and 36 and 16 and 1, 20, that's 70. Well, there's our 1, there's our 2, there's our 6, there's our 20, there's our 70. So the sum of the squares of the numbers on each row is equal to the middle element on row 2n. The row that's twice as far down if we start numbering from 0. And that's potentially kind of cool.
It was, if you just straight highlight the odd numbers, it looks like it's a good subtraction.
Okay, cool. I'll have to look that up. What else do we have? Well, we have ones all along here. Here we have consecutive integers. What are these things?
It's like u plus 2, then u plus 3.
Yeah.
Plus 4, but I don't know.
So these are the triangle numbers. 1, 1 plus 2, 1 plus 2 plus 3, 1 plus 2 plus 3 plus 4, and so on. You proved inductively this was n times n minus 1 over 2. So there's other symmetries in there. Here's my favorite one. So what's 11 to the 0? What's 11 to the first? What's 11 squared? What's 11 cubed? 1, 3, 3, 1. Bang, 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 bang. Guarantee you 11 to the fourth is 14,641. So we got powers of 11 in here by just reading across each row. It breaks down at this point because 10's not a digit, but if we work in a different base, this will still give us 11 to the fifth.
It kind of makes sense because 11, you kind of take one thing and put it on the other.
Yeah.
Side, and that's kind of how we're doing it.
Yeah, this is tied in directly to this idea that each number is the sum of the two things above it. Sort of. So this launched a former 215 student down a dark path of trying to develop a base infinity number system, because I made the idle comment that if you could work base infinity, then this would always work, and that was it. She was gone. She's doing machine learning now at OSU. Yeah. What is it?
161051.
Yeah. So
That'd be great, but like adding the digits, you would never want to add a digit if you were just infinity anyway.
yeah, yeah.
It's just a bizarre concept.
Yeah, it is. She came up with a weird system based on prime numbers. One aspect of which meant that when you looked at the representation of a number, you could immediately tell what its prime factors were, which means if a society developed under that base number system, they couldn't have a cryptography system like we have. And I was curious what that would do to like societal development if it was impossible to have secrets. But so that's Pascal's triangle. And there's some questions that ask you to play around with that a little. All right, questions? We got 4 minutes. Let me give you one other pigeonhole principle application. So given n plus 1 positive integers, each less than or equal to 2n, at least one is a multiple of another. So pick any number n, and pick n plus 1 positive integers less than or equal to twice n. And the claim is at least one of the numbers you pick is a multiple of another number you picked. So for example, let's let n equal 15. So we want to pick 16 numbers less than or equal to 30. And we want to try to pick 16 numbers so that none of those numbers divides any of the other numbers. All right, well, we could pick the number 2, but that's going to throw away all of our odd numbers. So we can pick 3 and 5 and 7. We can't pick 9. We could pick 11, 13, can't do 15, 17, 19, can't do 21, 23, can't do 25 or 27. We could do 29, and that's it. 4, 5, 6, 7, 8, 9, 10. We only picked 10 numbers. So that didn't work. We could start with 3, and now we can pick 4 and 5 and 7 and can't do 9 or 10, 11, and so on. And any way that you try to do this, it's impossible to pick 16 numbers without one of them dividing another. And this is true for any value of n. So if you try to pick 1,000 numbers less than or equal to 1,998, you're guaranteed at least one of your numbers will divide another. And it feels fairly plausible when you try to just work out a few examples. And you can try starting from the top end, right? Start with 29 and 28, and none of these divide each other. But that's as far as we can go. And we've got 6, 7, 8, 9, 10, 11, 12, 13, 14. We got 15 of them. And we got to pick one more number, and we can't. So we can prove this using the pigeonhole principle. So we'll spin through that proof really quickly tomorrow, but play around with this a little if you like. Prove this.
No, like that you can't have a number less than n plus 1. 1 plus 1 is 2.
There is a way to pigeonhole it. We'll go through it tomorrow.